Okay, good afternoon, everyone. Good morning, Bruno. Thank you again for accepting our invitation. I know it's very early for you, so it's very special thanks to you for accepting. Very eager to see your presentation. Bruno is going to talk us about autonomous driving and in particular interaction-aware motion planning in crowded dynamic environments. So he'll present the research he's done during his PhD. He was a PhD candidate at the University of Delft, so Delft University of Technology, and formerly he received his master's degree in electrical engineering from the University of Porto. He's also worked at the European Space Agency and at Fraunhofer Institute of Manufacturing. Currently he's a senior research scientist at Motional, which is a pioneer in driverless technology. So please, Bruno, when you're ready, you can start. We are looking forward to your presentation.
Thank you so much, Diogo, for the kind introduction, and thank you again for the invitation. I'm really happy to be here to get to know a bit about my work. But first, I'd like to introduce you to Motional. Motional is an autonomous driving company, and it was created as a joint venture between Aptiv and the Hyundai Motor Group. And our mission is try to make driverless vehicles safe, reliable, and access to everyone. So we want to reach all the ways on Earth. But this video will summarize better what we are trying to do.
What moves you? When people change the world, they call it a movement. Movement is power. It's opportunity. It's pushing forward, determined to create a better future. It's imagining the impossible, then making it real. It's what drives us. We are Motional, and we're making driverless vehicles a reality. The future of transportation starts now. We're focused on you, your choice, your safety, your community. We believe getting places reliably and confidently is your right. That's why Motional is changing how the world moves. Everyone's journey is different. And no matter where your journey takes you, we'll get you there. Motional. You move the world, we move you.
So now that you get to know a bit what we are doing, first I'd like to highlight that the research presented here was conducted at Delft and does not represent Motional's research. And so this is going to be what I'm going to talk today. First, I'd like to introduce you to model predictive control. Then I'll try to motivate you for the autonomous driving problem to clearly show you how challenging it is. And I'll present some autonomous navigation architecture that are typically used. I formulate the problem, and finally introduce two of my works, one on learning global guidance policies and on learning trajectory prediction models. So let's talk about model predictive control. So the way that we humans do or take decisions in the real world is we look at the environment and we are able to perceive how things are going to evolve. And based on this look ahead, we are actually able to take decisions that are optimal within the future time window. And let's make this more clear. So let's assume that we have a robot at T0, it's in this position, and we want the robot to follow this green path. So the first thing that we can do is we can take a sequence of control commands, and using the robot's model, we can actually compute where the robot is going to end up. So for instance, here we can actually initialize or plan over a prediction horizon where the robot is going to be if it will follow this sequence of commands. And if we have that, we can also define what is the error between what I would like the robot to do and the robot is actually ending if it will follow this sequence of control commands. And if we have that, then we can also define a cost function. And with this, we can then later use this cost function. It can be formulated as here. So if we plan n steps as is how it will look like. And we can also constrain this problem that in a way that the solution also satisfies the robot's model, for instance, here the speak with F. And if we have that, then we can use numerical optimization methods to compute what is the control command sequence that would minimize these errors. So in this way, we can actually find this control sequence that would allow the robot to follow this path. And the solution will be the feasible solution that actually satisfies also the robot dynamic constraints, so the robot model. And what we do in model predictive control is that we actually only apply the first control sequence. And why we do that is because in the next time step, we can actually collect new observations of the environment, and we can recompute a new sequence over and again, a new prediction horizon. So in that way, we can actually continue and recursively refine. Also, MPC is also known as receding horizon control. So these are two names that you may call it. And this is going to be one of the baselines that we use for motion planning. And that's why I wanted to use this concept first. So I know that in the past years, we did a lot of development in language translation model, perception planning. However, we didn't solve the motion planning problem, or autonomous driving problem yet. And why? As you can see here is the motivation of a highly complex environment where any technology existed today would freeze and will not be able to successfully navigate in this type of environment. And why? First, we don't explicitly communicate. And we, even without communication, we are able to coordinate with each other, which is quite impressive. Second, there is a high diversity of behaviors ranging from cooperative to non-cooperative. Even the same driver under the same severe situation, different times of the day, may react differently. So this makes the problem extremely challenging. And these environments are dynamic. So whatever assumptions you may do will be decided on environments, maybe today, maybe not tomorrow. You may rely on some assumption in structural environments, but if you aim to tackle all type of scenarios, then you need to really account that things may change. And the fourth one is interaction. So the way that we are actually able to navigate in such a dense traffic scenarios is by interacting with each other. And we are able to do that even without communication. So until autonomous vehicles are able to safely interact with humans, we will not be able to tackle this type of scenario. So to summarize, what are the current challenges? The first one is scalability. If you add more agents, and when I mean agents, I mean pedestrians, by other human-driven vehicles, as the number grows, the complexity also grows of the scenario. So this makes it extremely difficult. The second one, as I named before, is interaction. And the third one is long-term planning. We want to take decisions that are optimal in the long term and not in the short term. And this makes the problem harder. And the final is, how do we balance safety versus efficiency? Because if we want to be 100% safe, then we will never move. There is always a payoff that a vehicle has to take in order to navigate in this type of environments. So how do we balance this? How much do we accept to damage safety, to profit efficiency? So these are really current challenges that autonomous driving technologies are facing. And the first three ones together is what lead to what is known the curse of dimensionality. So this is what is makes problems really hard, and sometimes not be able to plan in real time. So now let's talk about planning and decision architectures. So there is three main trends. The first one is we use a hierarchical approach where we have perception algorithms, behavior, motion planning. Everything is clearly is developed in a separate way, so you can actually develop tests for each block and you really understand what is the task of each. And there is a second trend that mostly use either a navigation policy from simulation or from human-driven data. And in this type of architecture, they fuse the behavioral layer into the motion planning layer. And the third one is what is known as end-to-end planning. So you learn a policy that is able to map sensory input data directly to control commands. However, these methods, they are black box. There are a lot of efforts or research trying to make them interpretable, but we are still far from the interpretability that a structured approach has. And in this presentation, we will consider a hierarchical approach. So we will consider that each block, like perception, high-level planner, they are separate. And in here, I'll mainly talk about these three blocks. So local motion planner, that is based on MPC, the prediction model, and the behavioral layer is the third one. So let's define now the relation problem mathematically. So assume we have a robot at x0 time t0, and we want it to follow this end goal. So our goal also the environment of the robot is populated with other agents. So in this case, for instance, a pedestrian. And we want to plan this sequence of states or control commands that will allow the robot to get closer to its end goal. In order to do this in real time, we cannot plan infinite number of steps ahead. So we assume what is known as the limit planning horizon. So in a mathematical way, this can be defined as you see here on the left. So we want to compute this sequence of states and commands that minimize the final costs. That could be, for instance, a distance to the final position and end state position. And we also want to minimize the cost to go. Either we want to minimize energy, we want to penalize for acceleration, that smooth control. So this is how you define the cost to go. And you constrain your problem in a way that the solution satisfies the model dynamics of the robot. You also add the collision constraints to ensure safety. And you want to account for the state and actuator limits of your robot, given some initial conditions. So mathematically, this is what this scene represents. And the first one that we have here is if you have limit planning horizon, it means that you'll get only locally optimal solutions, which in the long term may lead to some catastrophic behaviors or deadlocks. And if you want to bring n towards infinite, so you want an infinite number of time steps, also the time to get the solution will go to infinite. So this is not, in the real application, you cannot do it. Another problem is that if you compute local optimal solutions, in this one, there is or they may exist more than one locally optimal solution. And how do you select between one or the other? It's also it's still an open problem. And another challenge is if you start adding more agents in the scene, as the number of agents grows, also then the time to compute the final solution also grows. So this is the fourth problem that you might find here. And the fifth one that I mentioned previously is interaction. So the policy of the other agents is not only conditioned on the robot state in its own state, but also on the actions that the robot may take and the other persons may take. So there is this coupling between the actions, which makes the problem really hard to solve. So you will see here, so if the robot does this motion plan, this will be the trajectory the pedestrian may follow. But if the person will do a different of the robot will do a different trajectory, the trajectory of the person will change. So how do you compute a solution that is optimal for both is also extremely hard. So now let's look at the state of the art and how people have been trying to solve this. On the left side, you see here a real application of optimization-based methods. So you see that the robot is actually able to plan ahead in time and to avoid these two pedestrians in the scene. The nice thing is that we can actually provide some safety guarantees here, and we can really account for the dynamics of the robot. On the other hand, we are limited to a limited number of pedestrians. Otherwise, you cannot solve the problem in real time. And we don't account for interaction. So if you add more pedestrians into the scene, the robot will just get stuck. This is also known as the freezing robot problem. On the right side, you'll see that you see a learning-based method. So it's mapping sensor data directly into robot actions. It doesn't have these scalability issues, can actually account for a high number of pedestrians, but there is no safety guarantees or feasibility guarantees. So there is also the sim to real gap. So if your environment differs much from simulation environment, the performance is going to drop significantly on your testing reality. And this may lead to, again, to collision. So it's not the same. And finally, you only learn reactive motion plans. This means that you only look one step ahead and you compute a command that will avoid the collision if necessary. But sometimes, because you have acceleration limits, this may be too late. On the other hand, the left side, you can actually do predictive motion plan. You can plan hand steps ahead and start hand steps in advance to do a collision avoidance maneuver. So the first way I'll present is how do we learn these global guidance policies and why are they necessary? The first one is that MPC, because there's this limit planning horizon, it requires global guidance. And on the other hand, as I said previously, RL does not satisfy necessarily hard constraints like safety and model constraints. So the idea what we propose is let's try to use deep reinforcement learning to learn this sub-goal recommendation policy and then use it as guidance for the MPC. And you'll see what is the motivation behind, because in this way, the MPC can actually handle all the robot dynamics, or when I say robot, can be autonomous vehicle or unalive robot, and the collision constraints, and the RL will take into account the interactions with the other agents and all these dimensionality issues. And why? Because RL actually allows to learn policies that maximize they maximize infinite time rewards. So in this way, you can actually take actions that plan much long ahead in time. On the other hand, the optimization-based method allows you to account for the model and the safety. So the combination of these two can be quite promising. And the idea is really inspired by BEMO optimality or dynamic programming. So you have this problem of planning towards a hand goal that is outside of your planning horizon. But this problem can actually be divided into planning, into breaking down the whole problem into small sub-problems where you plan to, in each sub-problem, you plan towards the optimum sub-goal. So in this way, instead of planning towards the end goal, if you know what is the optimal sub-goal and you plan towards it, then the composition of this, the optimal solution of the sub-problems will lead to the optimal solution overall. So that's why we propose to use reinforcement learning to compute this next optimal sub-goal, and we will employ optimization to drive towards this sub-goal, ensuring safety. So you can see here what is the main contribution. So we propose this goal-oriented multimodal control that is composed by a deep reinforcement learning agent that is generating these optimal sub-goals, also accounting for interaction between the other agents. And then this local motion plan that uses MPC to drive the robot safely towards these sub-goal positions. And the second contribution that we do is that we propose an algorithm that trains both jointly. So in this way, the DRL policy, when it gives a sub-goal and the reward we will get, is also constrained on the robot dynamics and on the real controller. And this allows us to actually deploy safely and easily a policy training simulation into reality. The sim to real gap here is minor. And so I'll now give you more details how we learn this policy. So we define our policies action space as the increment positions, and we limited these increments based on how many steps we want that MPC can plan ahead and its maximum velocity. So then this is how we account for this limited planning horizon. And we define our reward function. So we reward the robot when it reaches the end goal. We penalize if it collides with any other agent. And we also do a stepwise reward in a way that we motivate the robot to move towards the end goal as quickly as possible. Here you can see our policy network. So we fuse information from the robot state and all the other agent states. And one of the important contributions here is that we use this LSTM. So we input the other agent states as a sequence to the LSTM, and then we use the hidden state as information to represent all the other agent states into the network. And we do that because in this way we can actually input a sequence that may have a variable length, but on the other side, h of t is actually a fixed length into the policy network. So this is important. This allows us to actually tackle environments where the number of h's may vary over time, doesn't need to be fixed. And then once we concatenate this type of information, we fuse into fully connected layers. And we then split this representation into use two different layers, one to learn the value function, and the one on the top is where we learn the policy parameters. So we model it as a Gaussian policy. So we learn the mean and the variance of the increment positions that we want the robot to follow. On the other hand, on the MPC side, the low block, so this is how we account for the kinematic constraints into the problem, the actuator and state constraints, given the initial condition. And this is how we define the stage cost. So it's a penalty on the control command. So in this way, we want to have a smooth behavior. We want to, in here we use our control command is defined as the linear and angular accelerations. And by penalizing those, then we ensure that we don't want high acceleration values, so we will ensure a smoother motion. And as a terminal cost, we just define it as the distance between the end state position and the sub-goal provided the reinforcement learning agent. And finally, to ensure safety, what we do is we have a nonlinear constraints that ensures that the space of the robot defined as this disk does not intersect with the space of the other agents defined also as disks. So we use this nonlinear constraint to ensure that it will never overlap, and by never overlapping, we ensure that they never collide. So this is the overall algorithm that we proposed. We use here, actually use proximity optimization, but you could use also other methods like software critic. So what we propose does not depend on the RL algorithm. And there are two interesting points. The first one is that we use MPCs supervisor to warm start the policy. And why? Because if you start from a random policy providing subgoals, it's going to be really hard for the agent to reach any end goal position in the environment. And that will lead that it take a huge time for the policy to start learning what is optimal to start getting some successful lab results. And the MPC is actually good in simple environments. If you have a limited number of agents and you know what's your end goal, MPC can actually drive towards that safely. So we use MPC as an expert. So in this way, we don't need any human expert to provide or to warm start the policy. After that, we just use RL and we use a non-policy method that will just use the policy to correct rollouts experience, will optimize and get the new policy parameters. And in the next rollout, we will use new parameters that has just have been optimized. And this here you can see some training results. You see on top the evolution of the reward. And we compare our Go MPC method with deep reinforcement learning method and also MPC baseline. And you can see we also use curriculum learning. So over time, we increase the number of agents in the scene, so the complexity of the environment. And you see that actually both baseline, the RL and MPC, their performance goes down over time as the complexity of the environment increases. On the other hand, our approach is actually it starts to learn and in the end is actually able to achieve higher reward on average with 10 agents and the RL and MPC with just 2 agents. So we can really learn a policy that outperform both baselines. On the bottom, you see the average number of collisions, and you see that this number goes down. So clearly showing that our method is learning over time. So let's look at some qualitative results. So in this scenario, I'll pause it for now. You see on the left side, our free baseline, so our method, the RL MPC, swapping position with a non-cooperative agent on the right side. So this non-cooperative agent is moving towards the left, and our robot, following 3 different algorithms, moving to the right side. You can see that the MPC, because it has a limit planning horizon, I'll stop it here. It starts avoiding collision too late, and because of the kinematic constraints, it actually collides with the agent on the right side. On the other hand, the DRL, it can successfully avoid this collision, but it does it only at the last time step, so it does this wobbling motion around, which is completely non-smooth. And the interesting result is that our approach, it starts from the beginning to keep space to the other agents. And as it evolves, it sees that the other agent doesn't react to its position, then it just gives more and more free space. And once it crosses with it, it starts converging towards the end goal. And this is really similar to what you would see in a pedestrian. If you see someone rushing the corridor towards you, will just give it right away. And once it crosses you, you'll move again towards your end goal. So this was a first interesting result that we got. And here you can see how this approach scales to complex environments. So you see in blue, the agent is following our method. In green, is using a reciprocal velocity obstacle approach. So these agents are cooperative. And you see actually we can navigate in such a clustered environment. Even when we also add some non-cooperative agents into the scene, our approach is able to avoid these congestion areas, because all agents try to go straight away to their goal and they don't do any cooperation. So our policy is to reason about that and just go all around to avoid these congestion areas. And what we also tried is we had some agents doing these zigzag motion, some this weird motion that was not seen in training. And we see still that our policies can successfully navigate in this type of environments. And as a final thought, we also tried to plug in the same algorithm into a team of robots. So all of the robots here, they use this Go MPC approach. And they never saw during training agents following the same type of Go MPC policy. And this, the first time when we plugged in, this just worked. And this clearly shows the generalization capability of our approach. And please know that here the robots, they do not communicate with each other. The only thing that they know is about the other agent states. That's it. That's the only information that you know about their position, their velocity, and they can coordinate. We compared our approach with two deep reinforcement learning methods used to control multi-robot agents. And as you can see here on the left side, it's a reactive approach. So the agents go straight to the goal and then they start doing this close collision avoidance. The second one is the over-conservative one. You can see that the agents try to keep as much distance away from the others. Then our approach actually seems like an optimized version of both, something in between. So we believe that we are really close to the optimal solution for this problem. As a final result, I'd like also to show is that this type of ideas also scale to autonomous driving. For instance, in this, when you have these dense traffic scenarios and want to merge. In here, what we did differently, let me just speed that to the front. So you can see here on the main one, you see agents with, if they have high number and green color, they are highly cooperative. If they have low number, they are non-cooperative. They will not stop to give you free space to merge. And you see here, we are just learning to the MPC what is the velocity reference. And the nice thing is that you see the ego vehicle gets this interactive behavior that is when it's trying to merge into the main one, and is able to reason which agent is going to give free space or not. And this is really close to how we merge, how we tackle these things. So this is really interesting, because if you just use an MPC approach, the MPC will just get stuck. It will just consider that the agents will never be given free space, we will not be able to reason about the interaction among the agents, and will never be able to merge. While on the other hand, you see here this behavior, interactive behavior allows it to efficiently merge in this type of environments. So I think this finished my first part of the talk. So as a conclusion, so learning a sub-goal policy highly improves the safety of the robot in an environment with agents showing diversity of behaviors. It solves the scalability issues of trajectory optimization methods. We can actually consider an MPC with limited planning horizon, and we just consider also a limited number of agents in the surrounding, and allows to significantly reduce the complexity of this plan by reducing the horizon. On the other hand, combining deep RL with MPC approach allows to significantly speed up the learning performance. So this finished the first part. Now our method is also open source. If anyone has any questions so far about the method, something was not clear, something that would like to ask now, I think now it will be a good time for questions.
Yes, you can ask your questions now. You can either ask them in the chat, or you can raise your hand and just ask them. Microphone if you have one. So please don't be shy. Well, I have a question, so maybe I can start, and then people can think of the questions. So there you have shown. So in my understanding, you use like the MPC as a supervision signal for the VRL policy, so for starting learning VRL policy. But then what is not clear to me is, from what I can understand, at the end your solution will use RL, but it will use MPC on top of that. What I didn't understand is, how do you condition the MPC on the policy that the RL has already?
I see. That's a very good question. So I'll just go back in a few slides. See. So this is how we incorporate the DRL knowledge into the MPCs by providing this position reference in space. So the DRL tells the MPC where is the next sub-goal position or the next optimal sub-goal position. And the MPC drives towards that. So the MPC never really sees the end goal. The only thing it sees is what's the next optimal sub-goal. And then it's like, you can see it as the DRL just telling the MPC where to go. And
yeah, that's a very neat approach. Very nice. But so you can train them separately, right? So you can just train the policy first, and then you train the MPC on top of that, or you have to learn everything jointly.
so we could do that. So we could do that in a separate manner. But then the problem would be that you'll have the DRL telling the MPC positions that are not that MPC cannot read.
Okay.
So
Okay.
if you have this coupled way, so if you train them together, then the DRL, if it gives crazy position that MPC cannot read, will get penalized by that. And then the DRL will learn to give something that's actually within the limit of the MPC. But you could do that. You could then train them separately.
Mm-hmm. Okay. I think we have a question in the chat. Bruno, can you read it and answer it?
Yes, sure. How does this algorithm handle model mismatch in the MPC prediction model? Do safety guarantees solve? Well, that's a very good question. It's something that I didn't talk here. It was about the prediction model using MPC, because it's something that it's required by MPC to plan ahead. You need to have a prediction model of the environment. And so the way that, so we actually here we use a very simple prediction model that where there is definitely a mismatch between other predictions, the other agents do, and what actually the predictions provide. So we use a constant velocity model. We just assume that other agents will keep their velocity constant over prediction horizon. So in this case, this model mismatch is not a problem for the, let's say, for the MPC, because the DRL actually is able to learn these limitations on this model mismatch. So it's able to already to account on the sub-goal that it provides that the predictions are not entirely correct. And secondly, it's also not a problem for an MPC, because MPC is always planning towards a position within the planning horizon. And if you have collision constraints, and if you always start from a feasible solution, then you can always compute a solution that is recursively feasible. So you can always ensure guarantee if you plan always within, towards a position always within your planning horizon. So that's how actually we don't see any problems with this prediction model mismatch. The only problem that you may have is if you use a over-conservative model as constant velocity, is that you'll have over-conservative plans. Your policy may give you a position that's actually feasible and safe, but because the predictions do not account for the interaction, then you may have the robot will not be able to drive towards that position. So this is one of the limitations when you use simplified prediction models. I hope that I answered your question, João.
I think we have two more questions. Oh, sorry.
So the second one is from Thomas. How does MPC consider a varying number of obstacles in the collision avoidance constraint? That's a very good question, Thomas. Actually, in here, so what we did in the MPC, which is that we wanted to limit the complexity. So we just consider a limited number of agents in the neighborhood of the robot. So we bound these, we consider, I think, maximum 4 agents in the surrounding of the MPC. And then all the other agents are not taken into account. And this is where we actually lose these collision, these safety guarantees, because if you have within the planning horizon more than an agents, then we may actually collide. But this is where the DPRL policy is going to learn that this sub-goal that provided was not actually good, and it's going to be penalized by this sub-goal position. So this is actually the DPRL that is handling this variable number of agents. The MPC considers a constant and fixed number of agents. Then from Sukrit. Hi, Sukrit. Nice to see you here. Let me see, expand this. considering that there are sub-goal recommendation NPC involved, if we implemented this in a static environment, I am right in assuming that algorithm behavior will be similar to something like a smoother version of the RRT. Well, depends on the assumptions of your environment. But yeah, you could see it in that way. You could see it depending on from white agent. But actually, there is a variant of this work, something we present in the latest ICRA, where we actually use this approach to navigate in unknown environments. So you wanted to have these target positions within the environment, within the map, and we wanted to maximize exploration and also collect these target positions. So you could see that to use RRT in this type of methods, you will need to have a global map of your environment. But with this type of approach, you don't need it. You can actually build the map as you evolve in space. But you're right. So you could see it as if you have only static obstacles, then you and if you know the environment, then you could just use an RRT with another method to generate the control commands for the role. Okay, I think I answered all the questions. I hope that answers your questions, Brito and Thomas. And if that was clear, then I'll move to the second part of the talk.
Yeah, go ahead, Bruno.
Okay. Okay, let's now talk about predictions. It's something that I avoided so far, and a similar was given, but it's not. Because in reality, we don't know the other's plans. So if you want to plan ahead in time, you need to know what they are going to do. And this is also a problem. And I guess, so the way that you can see, so you can see here a problem in reality. So you see our mobile robots in our faculty core with 5 cameras, detects the pedestrians that are here represented on the map on top as circles. And you can see here that we use this constant velocity approach. We assume all the planning horizon, the speed is going to be constant. And the problem of this type of prediction is that first they collide against obstacles, which is not true. This may not happen. Secondly, they just predict that the pedestrian may run over against each other or over the robot. So this makes the robot highly reactive because the robot will just think that everyone will go on top of it. So we need better prediction models. We need to account for the environment constraints. We need to account for the interaction among the agents. So we need to find a way to solve the problem of this constant velocity model. So the way that prediction point can be formulated is also as a supervised learning method. So you can assume that you have this, you have a data set of recorded trajectories, for instance, of pedestrians. And if you have these recorded trajectories, then you can use it. You can take, for instance, a neural network or a parameterized model. And you can use that to either try to learn a mapping from the current state to the next state, or to learn a mapping from the current state and the next sequence of states. So in this case, will be a trajectory. So how the pedestrians may evolve in the scene over time. The problem was when I worked on these, most state-of-the-art approaches, they were purely deterministic. So they don't take into account the uncertainty of the agent's motion. And there was a second problem, that they didn't account for the multimodality. So human behavior is actually multimodal. You may avoid a collision on the left or on the right. And how do we predict both model trajectories was open problem still. And that's why we proposed the social VRNN model. So our goal was, how can we predict from one shot, looking at the scene, how can we predict multiple pedestrian trajectories? And the issue was that at the time there was some methods actually able to generate this model trajectory, but they required sampling. And when you randomly sample from your latent space to generate different trajectories, first, there is no guarantee that you'll get a different model trajectory. And second, once you get several samples, which sample do you account in your motion planning problem? Do you account for all? Do you account only for the samples that belong to different modes? So that was not clear. And that's why we proposed to use a variational learning to learn a Gaussian mixture model. And we would use this Gaussian mixture model to actually learn these multimodal trajectory predictions. And you can see here in the bottom the network that we propose architecture, but I'm going to detail that later on. So the network architecture was based on 3 main modules. So one in future extraction model, so where we're fusing different channels of information. Then we had this probabilistic inference module that was creating this weighted representation that was then fed into a decoder network that would learn this probability output module that was defined as the Gaussian mixture model. So let's look at the input. So we had 3 main channels. One, it was the pedestrian velocity. When I say here pedestrian, it can also be used for cars or any type of agent. And this pedestrian velocity was fed to an LSTM to learn this time-dependent representation of the agent dynamics. The second one was we fed a map of the environment. So by feeding this map, then we could reason about the environment constraints. So we used first an encoder network to minimize the dimensionality of the map. And then we fed again to LSTM to model the time dependencies. And finally, we also fed to the network the other agent states. So in this way, we also wanted to learn the interaction that there was between the agents. The second model, this probabilistic inference, this is based on in the autoencoder structure, so in the generative model, and there was 2 novelties. So first one is we didn't have any assumption on the prior parameters. We will actually learn the prior parameters over the latent space from a network model. So these prior parameters were also optimized within the model. And the second one is we incorporate also this skip connection from the input representation into decoder straight. So this allows also the gradients to propagate more efficiently towards the input representation module. And finally, our output module was a Gaussian mixture module to be able to learn M modes. So M was actually a parameter to define how many modes you want your model to learn. Of course, if you have only 2 and you find M larger, you'll have some modes that will collapse to each other and will be similar. But this is how this one of hyperparameter to typically define within your model or your problem. And each mode was modeled as a bivariate Gaussian. So in this way, we could actually also capture the motion uncertainty for each different model trajectory. So you can see here the results. We compared our approach against deterministic baselines and against these sampling-based baselines, so 2 state-of-the-art methods, SOFI and social ways. They were actually computing, sampling 30 trajectories and using the one that was close to ground truth for the error metrics. And on the right side, you can see our approach. You can see that actually our approach with just a single sample in a single shot could improve significantly performance compared to approach that was requiring 30 samples. So this is not only computationally efficient, it also simplifies your motion planning problem because you have a single trajectory prediction. And you can see here 2 qualitative results. On the top, you see agent moving from left to the right. We'll find an obstacle in the middle. And where there is nothing around, all the modes collapse. So you see all the predicted trajectories are all very similar. But when it finds an obstacle, it's actually able to find the 2 different paths that the pedestrian may follow. So here it go left or right. And as soon as the person picks one side, the actual modes go again to very similar. They get again very close because there is only one model trajectory in that scene. And you see here, so this reasoning about the environment or about the obstacles, but on the bottom, you see these blue points, there are other pedestrians, and you may see where they also get close, that you get these different model trajectories. So here actually you get the 3 modes, either going left, right, or even straight away. So this was highly interesting that our method could actually reason about these different model trajectories. And you can see also here in real environments. So you can see here 3 snapshots of 3 different real scenes where you can see the different model trajectories our model was able to predict. But I can also show it more in detail. So you can see, you get an idea about how the predictions look like. So these colored trajectories are the predicted trajectories, and in black is the ground truth of the model. So to summarize, variational learning allows us to significantly improve the prediction performance. We can actually account for interaction and static obstacles. And the overall, okay, before I go into the overall conclusions, is there any questions on the prediction methods? Is there anything that was not clear to you?
I think you can go on. Then at the end, if you have questions, they can ask them.
Okay. Then, as an overall conclusion, so I like to say that learning-based methods they allow you to learn high-dimensional models from large amounts of data, and this is highly significant. Is really important for optimization-based methods. It allows you also to improve not only the prediction performance, but also to improve the planning performance by providing this global information on decision variables of the optimization problem. So I've shown two different approaches, one on what is the next optimal position, and the other on learning this velocity reference and how we interact with the other agents. And to end up, so I like to say that we are hiring. So if you find these problems interesting for you and you like to contribute to the development of autonomous driving technologies, feel free to reach me out. We have several positions in our website. And yeah, if you have any questions, I'm glad to answer. And thank you so much all that were here attending this talk. And thanks again, Diogo and Priberam, for the invitation.
Thank you, Bruno, for accepting our invitation. Let's see if people have questions. I have one, just to start. In your results table, so you have shown two values for your model. You said that this was just with one sequence, but for this particular sequence that you have chosen, is it the most likely sequence, or is it a random sequence that you sampled from the mixture of Gaussians that you have here?
Yeah, that's a good question. Actually, I didn't detail on that. So the nice thing also when I didn't say when we learn this Gaussian mixture model is that we can also learn the likelihood of each trajectory. So in those results, what I used was the most likely trajectory predicted by our model. But again, I will also do highlight that I did some qualitative results, and sometimes these models get just overconfident on the training data. So it may put a high likelihood on just a single mode and really low likelihood on the other ways. So I think there is still research required to how do you reason properly about the likelihood of these trajectories. Because from my experience, the model was get highly confident in the likelihood of the trajectories. I'll chat.
Yeah, I think overconfident models are not to this problem. But yeah, there are some techniques to regularize it, but that's of course an interesting research question to address that. Let's see if we have more questions. Does anyone else have a question right now? Oh, it seems there are no more questions. So thank you very much, Bruno, once again for doing this very nice presentation. It was a very big pleasure to me, and I'm sure to the audience to attend this presentation. And a very special thanks again for accepting to do this so early for you. So everyone else, thank you for coming. We'll see. I'll see you hopefully not in 2 weeks this time. The next Priberam machine learning lunch seminar will be in 3 weeks exceptionally, and it will be the last one of this season. So make sure to attend it. And thank you again, everyone, for your participation.
Thanks, everyone. Thanks, Diogo. Have a good day.
Thank you.